In the quiet hours of the universe's infancy, when everything we now see was compressed into a searing sea of plasma and primordial light, nature forged the elements. It was a time before stars, before galaxies, before even atoms had cooled enough to form stable matter. In that chaotic soup of energy and particles, the first nuclei were born in what scientists now call Big Bang nucleosynthesis. From this fleeting cosmic furnace came the earliest elements: hydrogen, helium, and a dash of lithium. But as cosmologists peer deeper into space and further back in time, a strange discrepancy looms, one that refuses to conform, one that cannot be explained away. Its name is lithium. Not a black hole, not dark matter, not a distant quasar, but lithium, a soft, silvery metal familiar to anyone who has owned a smartphone or electric car. And yet, it poses one of the most enduring mysteries of modern cosmology. The Big Bang Theory has long stood as one of the crowning achievements of physics. It explains the observable expansion of the universe, the uniform background radiation left over from the early cosmos, and the relative abundance of the lightest elements. Its predictions are mathematical, elegant, and consistent, except for one. Lithium-7, the isotope expected to form in precise amounts during the universe's first 3 minutes, simply doesn't show up in the quantities predicted. Not even close. What's worse, lithium-6, an even rarer isotope, appears in far greater numbers than any current model can account for. This contradiction has come to be known as the cosmological lithium problem, and it sits like a splinter in the field of cosmology, nagging, persistent, and unresolved. To understand how big a problem this really is, we need to revisit those early moments of cosmic history. When the universe was less than 20 minutes old, the temperature dropped just enough to allow protons and neutrons to begin sticking together. This process, Big Bang nucleosynthesis, is one of the most precisely understood periods in physics. It predicts with near-perfect accuracy the amount of hydrogen, around 75%, and helium, roughly 25%, that we see scattered throughout the cosmos. These numbers align beautifully with what telescopes observe in ancient stars and interstellar gas. But when the same equations are applied to lithium, the results go haywire. The calculations predict about 3 times more lithium-7 than is observed. And lithium-6, that shouldn't be there at least not in the measurable amounts astronomers keep finding in ancient stars. The thing is, lithium isn't just important because it's chemically useful in batteries. It's a cosmic tracer. Its abundance acts as a fingerprint from the early universe. If that fingerprint doesn't match the print we expect from theory, then either our theories are incomplete or something in the universe is actively rewriting the evidence. And this isn't a small mismatch. It's not a rounding error. It's a glaring contradiction in one of the most tested scientific models in history. For years, cosmologists tried to tweak the numbers. Perhaps the nuclear reaction rates were slightly off. Maybe early stars burned through lithium faster than expected. But every time a new observational study came out, it only deepened the mystery. In some of the oldest stars, known as metal-poor halo stars, the levels of lithium-7 are shockingly consistent. This uniformity, known as the Spite Plateau, was initially thought to confirm Big Bang nucleosynthesis, but instead it highlighted the discrepancy. It's like taking dozens of blood samples from patients across the world and finding they all have the exact same rare condition. You begin to suspect that maybe the problem isn't with the patients, it's with your model of biology itself. Adding to the confusion is the presence of lithium-6 in those same ancient stars. Standard cosmology predicts that lithium-6 should be nearly undetectable in such early environments, perhaps 1 part in a billion relative to hydrogen. Yet it shows up thousands of times more often than expected. This flips the problem on its head. Not only is there too little lithium-7, but there's far too much lithium-6. It's a double violation, and it threatens to unravel a theory that otherwise fits the data beautifully. So what's going on? Some scientists have speculated that new, undiscovered particles might have interfered with nucleosynthesis in the early universe. Others wonder whether dark matter itself, still mysterious and unseen, could have played a role. Could exotic particles like axions or decaying supersymmetric particles have altered the elemental ratios? These ideas remain speculative, but tantalizing. Because if the lithium problem can't be solved within the known laws of physics, then those laws may need to be rewritten. That's a terrifying prospect for some, but an exciting one for others. After all, great leaps in science often come not from answers, but from persistent, inconvenient questions. But there's another possibility, one that doesn't require new physics, but new interpretation. Maybe we've been looking in the wrong places. The lithium measured in ancient stars might not be as pristine as we think. Stars are complex, violent machines. Their interiors churn with fusion and convection. Surface lithium can be depleted over billions of years. Or perhaps it's produced through previously unknown mechanisms involving cosmic rays or stellar flares. What if our assumption that these stars reflect the untouched chemistry of the early universe is flawed? That would mean the lithium problem is not a window into new physics, but a mirror showing the limits of our methodology. Yet even this more conservative idea has its issues. The consistency of lithium levels across multiple old stars in different regions and galaxies is hard to explain away with stellar dynamics alone. It's not just that one or two stars are outliers, it's a pattern, a global one that spans across time and space. And that kind of uniformity demands a deeper explanation. The tension has sparked an ongoing debate among cosmologists, astrophysicists, and particle physicists. Some argue for the need to revise our nuclear reaction models. Others propose pre-Big Bang mechanisms, or the possibility that the universe didn't begin with a singularity at all. Even Stephen Hawking, toward the end of his life, suggested that quantum effects might eliminate the singularity at the heart of the Big Bang model entirely. That idea, combined with new research in quantum gravity, hints at a more complex and nuanced origin of our universe, one that could account for the lithium anomaly in ways we haven't yet imagined. The mystery remains unsolved. And in the meantime, lithium continues to taunt us from the specter of ancient stars. Its quiet defiance a signpost that something is missing, something crucial. Whether it's a gap in our understanding of the cosmos or a limitation of our tools and assumptions, one thing is clear. Lithium is more than just a battery material. It's a cosmic puzzle piece that doesn't quite fit. And until it does, the story of the universe will remain incomplete. If lithium were just an isolated data point, something astronomers could file under anomalous readings and move on, the problem might have faded into the footnotes of cosmology. But lithium is stubborn. It keeps showing up in the data, in telescopic observations, in spectral lines traced back to some of the oldest known stars. Every time a new survey refines the precision of its instruments, the mismatch between theory and observation remains. It doesn't shrink. It doesn't blur into the noise. Instead, it sharpens like a blade, cutting through the assumptions that have long been treated as settled science. And that's what makes it dangerous. Not because it breaks the theory outright, but because it threatens to expose the cracks beneath the surface, the foundational assumptions that haven't been re-examined in decades. There's a paradox here. The Big Bang model, for all its elegance and observational success, is built on extremely narrow windows of evidence. Cosmic microwave background radiation. Yes, that's a victory. Hydrogen and helium ratios. Again, very much in line. But the lithium problem reminds us that even one discrepancy in the early universe's fingerprint could point to a much larger issue hiding in plain sight. It's as if we've constructed a cathedral of knowledge on top of one cracked tile, and only now are we noticing the tremor beneath our feet. This situation has prompted cosmologists to split into several camps, each with their own preferred explanations, some conservative, others revolutionary. On one side are the astrophysical realists, who argue that lithium's scarcity and overabundance can be chalked up to stellar processes. These researchers propose that lithium-7 has been destroyed over billions of years by mechanisms such as rotational mixing or diffusion in a star's outer layers. Maybe the lithium we expect is there. It's just been buried too deep for our instruments to detect. Similarly, perhaps lithium-6 is being created by cosmic rays colliding with nuclei in the interstellar medium, a process known as spallation. In this view, the universe is still playing by the rules. We just haven't fully decoded its behaviors. But the problem with this interpretation is that it requires multiple overlapping adjustments to otherwise reliable models of stellar evolution. And yet, across numerous stellar populations, even those in completely different galaxies, the lithium levels display the same anomalies. If stellar destruction or cosmic ray creation were the dominant forces, we'd expect a broader scatter of results. Instead, we find uniformity, again and again. That uniformity is both puzzling and deeply suggestive, as it points not to localized stellar processes, but to something imprinted on the universe itself, something from its earliest moments. That's where the more radical theories enter. One class of solutions invokes new physics, exotic particles and interactions that either don't exist in the standard model or remain undiscovered. For instance, some propose that massive decaying particles, perhaps remnants of supersymmetry, could have interfered with primordial nucleosynthesis, modifying the neutron to proton ratios or altering reaction pathways. Others suggest that time-varying constants, like the strength of the nuclear force or the speed of light, may have been different in the early universe. If the fundamental constants were even slightly altered during that first critical window, the predicted abundance of lithium could shift dramatically. These ideas are bold, speculative, and difficult to test, but they also breathe new life into theoretical physics. Another intriguing avenue comes from quantum cosmology. In conventional models, the Big Bang is a singularity, an infinitesimally small point of infinite density and temperature. But quantum gravity, the yet-to-be-completed theory that would merge general relativity with quantum mechanics, suggests this singularity may not have existed at all. Instead, the universe might have undergone a bounce, a compression followed by expansion. Or perhaps the universe was birthed from a quantum fluctuation within a broader multiverse. In such frameworks, the initial conditions could vary significantly, allowing for different element abundances, including lithium. Stephen Hawking, near the end of his career, began advocating for a no-boundary proposal, suggesting the universe didn't have a singular beginning, but emerged smoothly from a quantum state. If that's true, it could potentially alter the timeline and dynamics of nucleosynthesis, offering a loophole in the current lithium predictions. In essence, lithium becomes not just an element, it becomes a gateway to probing the most fundamental questions about time, space, and reality itself. The irony is that for all its theoretical complexity, the lithium problem has persisted for decades precisely because it appears so simple. Lithium isn't exotic. It's not some distant quasar or elusive neutrino. It's a metal used in laptop batteries and psychiatric medication. It's something tangible, familiar, and yet it's become a symbol of cosmic defiance. In a universe that largely behaves according to our expectations, lithium refuses to comply. This raises uncomfortable philosophical questions about the scientific process itself. When a model is as successful as the Big Bang, it becomes difficult to question its components. It accrues authority through repetition and confirmation, but science is not a religion. It is not meant to bow before its own history. When evidence contradicts theory, the theory must evolve, or eventually fall. That's what makes the lithium problem so compelling. It reminds us that science must always remain open to doubt, even when that doubt comes from something as deceptively ordinary as a metal. Some researchers have proposed entirely new cosmological models that abandon or modify the Big Bang framework altogether. One such idea is the cyclic universe, in which the cosmos undergoes an eternal series of expansions and contractions. In this view, what we think of as the Big Bang was just the latest iteration in a much older cosmic dance. If this were true, the conditions for element formation might vary from cycle to cycle, introducing anomalies like the lithium problem. Others have explored the idea of asymmetric dark matter, particles that behave differently from regular matter in a way that subtly changes the early nuclear reactions. Or perhaps the lithium problem is a clue that baryogenesis, the process by which matter came to dominate over antimatter, played out differently than expected. These are not minor adjustments. They are paradigm shifts, the kinds of theories that demand new physics, new observations, and new instruments to test. And therein lies a final, humbling truth. For all our equations and models, we are still observers perched on a single rock, peering out into a cosmos we barely understand. Our tools are improving: spectrographs, space telescopes, particle detectors, but they are still limited. We are trying to reconstruct the infancy of the universe from the dim light of stars that are nearly as old as time itself. Any measurement we take is filtered through layers of assumptions, calibration errors, and cosmic dust. It is entirely possible that lithium is whispering to us, but we are simply too deaf to hear the full message. Still, the pursuit continues, because cosmology is not about easy answers. It's about difficult questions. And lithium, for all its defiance, may yet lead us to a deeper understanding of the cosmos. It's an element caught between worlds, between theory and observation, between the known and the unknowable, and that makes it more valuable than gold, more significant than any quasar or galaxy cluster. Because it's not just an anomaly, it's a clue. And clues, when followed with care and curiosity, have a way of revealing the deeper story, one that might change everything we think we know about the universe. There's something uniquely unsettling about standing at the edge of knowledge and staring into the unknown. Not a lack of data, not even a lack of technology, but a precise and persistent contradiction that science cannot explain away. The lithium problem, in many ways, is not just a question of atomic abundance. It's a cosmic riddle, etched into the oldest light and the oldest matter we can observe. It's as if the early universe is whispering back, "You've missed something," and the silence that follows is deafening. So where does that leave us? In laboratories across the world, researchers are still chasing answers. Particle accelerators are probing the behavior of rare isotopes under high-energy conditions. Radio telescopes are mapping lithium signatures in distant stellar halos. Space missions like Gaia and the upcoming PLATO telescope are refining stellar models, trying to unlock the chemical history written into the light of ancient stars. And yet lithium continues to evade reconciliation. It remains quite literally the inconvenient element, one that stubbornly refuses to match the script laid out by our most trusted cosmological story. But perhaps the lithium problem is not a failure. Perhaps it's a gift, a sign that we are still on the path of discovery, that the universe has not yet surrendered all its secrets. After all, it is anomalies like this that have historically triggered some of science's greatest revolutions. The orbit of Mercury's perihelion didn't match Newtonian mechanics, and out of that emerged Einstein's general relativity. The spectral lines of hydrogen didn't match classical predictions, and from that mystery came quantum mechanics. Each time a contradiction became a catalyst. Could lithium be next? One provocative theory suggests that the problem lies not in the universe, but in the very way we interpret evidence. Cosmology, despite its deep mathematical rigor, is still a narrative, a framework of cause and effect constructed from patterns in the sky. But it is also an exercise in inference, extrapolation, and philosophical assumption. When we look at a star billions of light years away, we don't see it as it is. We see it as it was. We are always watching ghosts, always reconstructing history from relics of radiation. And if even a single variable in that reconstruction is off, whether it be a miscalibrated model of stellar convection, an undiscovered neutrino interaction, or an unaccounted for process in nuclear decay, then the entire edifice built upon that data can sway. Lithium, for all its mass of just 3 protons, could be the pebble that shifts the entire mountain of cosmological theory. Some have even questioned whether our interpretation of spectroscopy, the primary tool for determining element abundances, is as infallible as we like to believe. These methods, after all, are incredibly sensitive to stellar temperature, metallicity, and line-broadening effects that can vary subtly across different observational environments. If our measurements of lithium in metal-poor halo stars are skewed even slightly, it could radically alter the conclusions we draw. And yet, even after repeated refinements and recalibrations, the discrepancy remains. It's easy to forget that the universe does not owe us clarity. Our theories are maps, not the terrain itself. They help us navigate, but they are never the final word. The cosmos is under no obligation to be simple, elegant, or even understandable. And perhaps that's what makes the pursuit all the more beautiful. There is also a deeper, almost poetic irony in the fact that this cosmic mystery revolves around lithium, an element whose modern relevance is tethered to our digital age. It powers our smartphones, our laptops, even our electric cars. It's a metal mine from the earth, refined for commerce, and yet it may hold the key to understanding the first 3 minutes after time began. It is a thread that connects the practical to the primordial, the consumer to the cosmological. And perhaps that's the most profound lesson of all, that in the most mundane elements of existence, there are echoes of the universe's birth, that every atom we touch is a relic, a remnant, a piece of that first great fireball. Lithium, in its disobedience, invites us to question the creation story itself, not to dismiss it, but to refine it, to elevate it, to recognize that even the most cherished models are only temporary scaffolds for something truer, deeper, waiting to be discovered. Some cosmologists have taken this as an invitation to reimagine the birth of the universe entirely. They propose models where the standard nuclear processes we understand were just one act in a longer, more complex drama, one perhaps involving asymmetries in time itself, or feedback loops between matter and spacetime that we have yet to formulate. Others suggest that our universe might not be closed, isolated, or even alone, that perhaps these anomalies are signals from beyond our observable horizon, from neighboring universes with different physical laws, subtly tugging on our own like gravity, distorting the edge of a black hole. In that light, lithium's defiance becomes a message from the multiverse, not one that contradicts science, but one that invites us to expand it, to think beyond what we know, to question the limits of our imagination. And yet, for all the grand speculation, the scientific process remains grounded. New generations of telescopes, such as the James Webb Space Telescope, are poised to offer even more precise measurements of early stellar populations and interstellar gas clouds. Future missions may finally detect primordial lithium directly, free from the confounding variables introduced by stellar aging and mixing. And with each new data set, we move closer to the truth, whether it confirms our models or demands their reinvention. What makes the lithium problem enduring is not that it invalidates the Big Bang. It doesn't. But it suggests that the story is incomplete, that there is a chapter missing, a paragraph torn from the first page of the universe's history. Maybe it's new physics, maybe it's observational error, or maybe it's something no one has even thought to ask yet. But the question remains, glowing faintly in the spectral lines of ancient starlight. Why is there less lithium than there should be? It's a small question, deceptively simple. But like all great questions in science, it carries within it the potential to upend everything. And that's why it matters. Because in the end, science isn't just about answers. It's about the willingness to ask better questions. It's about humility before the unknown, the discipline to doubt, and the courage to revise even the most sacred theories when the evidence demands it. Lithium, for all its inconvenient stubbornness, is a reminder of that ethos. So the next time you glance at your phone or plug in your electric car, remember this. Inside the battery is an element forged in the fire of creation, older than Earth, older than the stars themselves. And despite everything we think we know, we still don't fully understand where it came from or why it's missing. And maybe, just maybe, that mystery is the most honest reflection of our place in the universe. Not as masters of knowledge, but as seekers, as storytellers chasing the truth in the dark, guided by the faint glow of something small, silent, and profoundly cosmic.